In this video, I'm going to talk to you about quantum numbers. Now, the last couple videos, I've been laying a foundation for you to begin to understand quantum theory and the quantum mechanical model for the atom. And this is based on this particle-wave duality. The quantum numbers are a unique set of four numbers that describe both movement and the trajectory of an electron. Now, this is within the atom, and it is based on quantum mechanics and the quantum theory. Okay, now, what's incredible is these four numbers can determine the electron configuration of an atom, which is something I'll be talking to you about in the next video, and the probable location of an atom's electrons, its ionization energy, and its atomic radius. It is a unique set of numbers, and they denote one electron. All of this information about one electron in one atom, and no two electrons share this same set of unique four numbers. So here are the four quantum numbers. There's the principal quantum number, the orbital angular momentum quantum number, which is denoted with an L, the magnetic quantum number, denoted as M sub L, and the electron spin, denoted as M sub S. Here you can take a look at the four numbers and the what they kind of mean. I'm giving you a visual here, but essentially one is the distance, all right, and that's that principal quantum number. One gives you the shape. Remember all those shapes we discussed in the last video. One gives you its orientation in space, actually where it resides within orbitals. And the last one gives you the spin of the electron. All right, so I'm going to explain all of this. Let's go through them one by one. Principal quantum number. All right, so this is the size of an atomic orbital. So I want you to find your periodic table because we're going to make some notes on that here in a minute. But it describes that probable distance that electrons are from the nucleus. How far away is one electron from the nucleus? Think of the energies, think of the levels. The larger that distance is, the larger the principal quantum number is. In other words, a quantum number n equals 3 has a greater distance than n equals 1 from the nucleus, okay? Which means it has a larger orbital and therefore is a larger atom. N can be any positive integer. There's those discrete units again. When I talked harmonics, I said the fundamental harmonic, n equals 1. The second harmonic, n equals 2. Well, n equals 1, n equals 2, also for the quantum numbers. Okay, that also applies. All right, periodic table time. So in the last video, I asked you to kind of somehow denote the S, the P, the D, and the F blocks. Okay, so here it is again. I want to show you where these energy levels are, where the quantum numbers are. So in the very top, next to hydrogen, that is the first energy level. That is the principal quantum energy level 1. Okay, and it goes all the way down the group to 7. So when electrons are at ground state, the largest n can be is 7. Now when they're in excited states, they can actually go beyond 7, which is beyond the scope of what I'm trying to do here. Okay, so hydrogen and helium are both going to share the same principal quantum number, n equals 1. But remember, there's 4 different numbers here. Okay? So this would extend all the way across. If I were to say, which elements will have principal quantum number 1, you would say lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon are all going to have that same principal quantum number, n equals 2. All right, the second quantum number is the angular momentum quantum number, denoted with an L. And it is going to determine the shape of the atomic orbital. We've started talking about shapes in the last video, and you saw all of those different orbitals, especially when we got down into the F block. They were pretty intense. All right, each value of L indicates a specific subshell. All right, so S, P, D, and F. And I went over those in the last video. One shaped like a sphere, that's the S. One shaped like a dumbbell, that's the P. One is shaped like a clover, that's the D. And one is just kind of crazy, and that's the F. But bottom line is, they are all unique. So if we were to assign an angular momentum quantum number, we would assign a 0, 1, 2, 3. Okay? So remember the S orbital. I tried to give a little intuition in the last podcast about that. All right? So the angular distance isn't going to change. That's why it's given a 0. It is shaped like a sphere. Okay? Whereas the other orbitals are going to have different shapes. All right? So let's take a look at our periodic table again. And go ahead and label these. S equals 0, P equals 1, D equals 2, and F equals 3. All right, so those numbers are going to correspond with the shape. Remember what we're going to end up with here. 4 numbers that will describe in space 1 electron and 1 atom, and no 2 electrons are going to share these same 4 numbers. Okay, so let's do an example. If n equals 3, then what would be an acceptable value for L, the angular momentum quantum number? So n equals 3. Let's find n equals 3 on the periodic table. Okay, so that entire period is going to be in this third energy level, this third shell. Okay, within this shell are subshells, S and P. Okay, and within the P are orbitals. Both have orbitals, but P has more than one. Okay, all right, within this one energy level. So n equals 3. What kind of shapes can we have? Let's put it in a term. What kind of shapes? Well, if n equals 3, then L could equal, let's look at sodium. Sodium's in the third energy level, and its shape here is a sphere S, okay? S is a 0, okay? So it could be sodium, all right? What if it's not? What if it's another compound? What if it's silicon? All right, what if it's silicon? Then in that case, it's not going to be a 0. It's in the P block, which is given a 1. Okay, so it could either be 0 or 1. Those are our acceptable answers, 0 or 1, because we don't have enough information other than what energy level we're in. N equals 3. So it could be sodium, could be silicon. Regardless, it could be a spherical S, or it could be the P, the one that's shaped like a dumbbell. Okay. The third quantum number is the magnetic quantum number. So this is the orientation of an electron in space. All right. This is within an atomic orbital. Okay. An atomic orbital. So I'm going to talk to you about that. And if you're not following, remember what I asked you to do a couple videos ago. Bear with me. It's all going to come together, I assure you. Okay? So, given these numbers for L, M sub L is going to be an interval. And it will range from negative L to positive L, including 0. All right? So it can be a negative integer, it can be a positive integer, or it can be 0. Let's look at an example here and try to make some sense out of this. So here's the S orbital. We know L is equal to 0. N could be 1 through 7 at ground state. L equals 0. So if there's 0 angular momentum, then the magnetic quantum number is also going to be 0. So anytime you're dealing with an atom and we are in the S block, regardless of what the principal quantum number is, if that shape, if that magnetic quantum number, if the angular momentum quantum number is 0, the magnetic quantum number is also 0. And that'll make more sense when I talk about the P subshell. Okay. So if we look at the P subshell, we have on our Cartesian plane this x, y, z. All right. And based on the angular momentum and the difference in angle from these axes, we get these different shapes. All right. Now, on top of that, we also have this three-dimensional thing going on here as well. So each one of these represents a distribution of an electron. So remember that animation, they're kind of just moving around, all right? And there's another one over here. So within this subshell, we have these two orbitals. Okay, or two electrons can fit in that one orbital, Then we have another orbital in the Y. Again, same thing, two electrons. Okay, 90% distribution probability. There's a 90% chance electrons will reside within this region, okay, within this region. All right. Then we have our third dimension of Z, same deal, two electrons. All right, so this particular quantum number can range from minus to positive. So what's L equal to for P? What's L equal to for P? 1. All right, remember S is 0, L is 1. P is 1, S is 0, D is 2, F is 3. Okay, so we have here L equals to 1 because this is the P subshell. And within the P subshell are these different orbitals. And within these different orbitals, each can hold 2 electrons. So this quantum number is telling exactly where the electron is located within the P subshell. Okay, so if we have L equals 1, then acceptable values for this would be -1, 0, +1. Okay, so conventionally, the Z is denoted as that 0. Okay, and then X and Y, -1, +1. but it is actually far more complicated than that. And it involves some mathematics that are well beyond the scope of what we're doing here. But that kind of gives you an idea. So 0, -1, +1. All right, so these are the areas or the orientations in space on that Cartesian plane where electrons reside. Okay, now let's look at this example. So we have n equals 2, L equals 1. What is an acceptable value for the magnetic quantum number? Okay, so if we're in the second energy level, this could be, say, beryllium, but it could be nitrogen. All right, so L could, or M sub L, could equal 0. Because if it's in the second energy level, like beryllium, beryllium's orbital is spherical shaped. It's an S. S equals 0. If S equals 0, L equals 0. Okay? Or M sub L will then also equal 0. Okay? So all of those will equal 0. But if L is equal to 1, as it is here, it could be this, this, or this. Okay, so really our acceptable values would be, any of these would be acceptable. And again, I'm going to write it down one more time. 0, -1, +1. When we're dealing with the p subshell within those orbitals, these are the orientations that electrons could possibly have. The fourth number is the spin. All right, M sub S, and it's telling us basically how the electrons are spinning, okay? And good news, they can either be spinning up or spinning down. And this has been experimentally shown. These electrons, these tiny subatomic particles are spinning, actually generate a tiny magnetic field, all right, that are oriented opposite. Okay, so energetically speaking, it's a lower energy scenario if these two negatively charged subatomic particles are going to be in the same orbital. Okay, remember, like charges repel, all right, but they are going to be in the same area. Then one spins one way, one spins the other. Think of magnets or something to help you conceptualize this a little bit. And we denote that as either a positive 1/2 or a negative 1/2, depending on the spin. Okay, it's been shown experimentally that these magnetic fields are generated within shells and subshells and orbitals. All right, so let's look at example number 3, which is the last example in this video. List the possible combinations of all 4 quantum numbers when the principal quantum number n equals 2, the angular momentum quantum number L equals 1, and the magnetic quantum number M sub L equals 0. Get out your periodic table, find shell energy level 2. Now find the P block, because that's what L is telling us. We are in the P block. Okay, so you are in the period with boron, carbon, nitrogen, oxygen, fluorine, and neon. Moving on to the third number, we're told that the orientation is 0. On the Cartesian plane, that was in the Z, okay? In the Z dimension. And within the Z dimension, within that one dimension, we can have 2 electrons. In that orbital, if 2 electrons are present, one will have a positive up spin, and one will have a negative downward spin. Okay, So one will be spinning around this way, and one will be spinning around this way. One is going to have a positive 1/2 value. One is going to have a negative 1/2 value. And we do not know which one it is. So the first three quantum numbers would be the same. And the only difference would be it's either plus 1/2 or minus 1/2, which means it's either going to be carbon or fluorine. And if you're wondering how to tell, ask me in class tomorrow. I would love to go over it with you. But before we get to electron configurations, I'm going to leave it at that. And what I want you to get out of this entire video is using quantum theory and the quantum mechanical model for the atom, we can apply quantum numbers, a unique set of 4 numbers that only one electron in one atom will have. So today's video delved into some College Board big ideas, dealing with the quantum mechanical model and looking at electron configurations. There are also some commonalities in our Georgia Standards of Excellence, but as you know by now, I like to go above and beyond. I'll see you guys in class.